Okay. Hello, thank you for being here. This is Joaquin. The topic of my presentation today is multi-link, multi-AP coordination-based joint transmission for seamless roaming in IEEE 802.11 Let's see the overview of this presentation. I will divide my presentation into three parts. First, I will discuss introduction and motivation. Next, I will talk about our proposed method. Lastly, simulation results and conclusion we are going to look at. The presentation will focus on proposed method and simulation results. Let's start with introduction and motivation. I would like to talk about UHR. UHR stands for ultra high reliability and is a proposed standard to increase the performance with a focus on the user experience, as opposed to the traditional Wi-Fi version. Wi-Fi A presents four main use cases in this table. For the data rate, we showed that it can be met with the multi-link operation proposed in Wi-Fi 7. However, with Wi-Fi A, it appears that close to 100% performance is required for reliability. MLD is a technology that can be applied to multi-link device with more than one wireless LAN interface. The AP to which MLD is applied is called AP MLD, and the user device is called non-AP MLD. MLD refers to a technology in which two or more MLDs form multi-link for data communication. The MLD technology is revolutionary for wireless LAN, but there are some issues. There is load balance, spectrum inefficiency, and MLD-only handover. It's the main problem in my thing. There is MLD-only handover inefficiency. I'd like to illustrate this by showing you the next page. I'd like digress here for a moment and just mention the meaning of handover and roaming. In this presentation, I will use the terms roaming and handover equally. This means that I will refer to a connection changing as a device move through AP coverage. From my research into IEEE standard contributions, it is clear that roaming is used more often than handover. Okay, let me go back to what I said earlier about MLD-only handover issues. When a handover occurs, the user device must unlink from the AP MLD to which it is connecting. This process can result the data loss and latency. And in the worst case scenario, in environments that require real-time operations, data can be transmission and received incorrectly. I have considered why do non-AP MLDs have to unlink all of their link and link to the next AP MLD, and can't non-AP MLD just unlink one end connect to the next AP MLD first? So I propose the multi-link, multi-AP coordination-based joint transmission method. It is our view that use the multi-link efficiency and communication with multi-AP coordination. The non-AP MLD is in communication with AP MLD1 using multi-link in use. The non-AP MLD then attempt to go beyond AP MLD1 BSS. For simplicity, we assume that STA 1, 2, and 3 use 2.4, 5, and 6 gigahertz respectively. When a non-APMLD is located in the OBSS of APMLD 1 and 2, APMLD 1 will share the information of the non-APMLD with its neighboring APMLDs. The non-APMLD recognizes it is located in the OBSS of APMLD1 and release one link. I want to be clear that we are saying that non-APMLD are located in the BSS. This is monitoring RSSI, and when it falls below a certain threshold, the non-APMLD will then connect with APMLD2 using a link in the 2.4 gigahertz bandwidth. This is the most adaptable link for the dynamic current network environment, even if the data rate is low. If 2.4 gigahertz is busy, it will use the lowest available bandwidth. This figure shows a simplified representation of the proceeding process. In A, the non-BSS non-APMLD is located in the OBSS, and the APMLD1 shares the information of the non-APMLD. And in B, the non-APMLD leaves BSS1 completely, and the non-APMLD communications only the APMLD2 in BSS2. In the case of a joint test mission, the APMLDs that are connecting monitoring the RSSI and definitively conclude that the non-APMLD signals is weakening. During this process, the connecting APMLDs A and B share information about the moving non-APMLD by sending a JT ready signal to the neighboring APMLDC. The APMLDC identifies the currently available band over the link and determines that the non-APMLD is coming OBSS. APMLDC determines the band over the currently available link and connect using the 6 gigahertz band, which is the roaming link of the non-APMLD. This allows the non-APMLD to experience the seamless handover. Now let's move on to simulation result and conclusion. The table 2 is the CSM parameter in our simulation, and let's figure this is simulation environment. The black line is movement of target user, and the green vertical line, this is where the AP changes or crosses of the BSS. I'd like expand on this offset QoE. We measure QoE using 5 performance metrics. These are throughput, latence, packing loss, jitter, and handover success, which quantify the overall quality of experience a user feels. And the network environments we simulated are as follows. First, single link, single AP is a transitional network environment. Second, single link, multi AP is an extreme network environment for comparison. There's the MLO are done applied. Finally, our proposed method networks. Okay. In a single link, single AP environment, we see consistent decrease in throughput here. At the point where the target users goes beyond the coverage of AP, this causes data loss and reduces handover reliability. This here. The most severe performance reduction occur in network with only multi-AP. This is because the AP MLD has identified the target user, but there is no link left for handover. So from the AP MLD's perspective, handover reliability is significantly reduced. And our proposed method is the clear-best option in terms of handover performance. It offers the highest handover reliability from the AP MLD perspective. We can see the handover reliability maintained even if non-AP MLD crosses the BSS of the AP MLD. This is for two reasons. First, if the non-AP MLD is outside of the BSS or AP MLDs, it is excluded from the performance measurement. Secondly, handover reliability is measured as non-decreasing as the link is continuously connected, which is the same for a simulated environment. My research shows our proposed method has the highest performance, and a key problem is that multi-AP should not be used without MLO. The evidence is in the results of single link multi-AP. In fact, despite using multi-AP, it has the lowest performance due to its high complexity and the limitation of the single link used by the target user. I think that MLOs on their own are a great performance enhancer, but multi-AP alone are a performance degrader. Okay, I'd like to conclude by summarizing this presentation. First, I covered in transitional and multi-AP only network environment the constraints of single link cause performance degradation. Then we talked about multi-link, multi-AP coordination-based joint transmission method can achieve high performance in the performance metric of user experience. However, the network complexity may increase due to the coordination between AP MLDs. In addition, in congested network scenario with multiple multi-link ML operation, the interference problem caused by non-AP MLDs may increase. Okay, today I have shown you multi-link multi-AP coordination-based joint transmission method. However, it also has a few limitations. We will be testing different learning techniques and the future to address these limitations. Okay, these are my reference. Thank you very much for your attention.